to.
This call is now being recorded.
Okay, recording has started. This means that the other feature is not also here. Okay. Okay. All right. So let's go now. So today we are looking at magnetism. So magnetism, first of all, is obviously depends on magnets. So we're going to answer this question: that what are magnets really? So we're going to say magnets are a material or an object that produces a magnetic field. It is an object with dipoles. Dipoles means two poles. Right. So now what is exactly a dipole? Let's see. What is a dipole? So for dipole, basically it's a region in a material that is polarized. Now, I just want to tell you, if you take a magnet, suspend it freely. Let me write that down. A magnet suspends freely, begins to move and oscillate. Its north pole gets attracted to magnetic south of. Why do Yes. Oh my god. It basically, North Pole gets attracted to magnetic south polarity of the Earth. Alright. So it aligns with Earth's geographic north. By the way, you might be thinking, or maybe you know already, this could be true. You might be thinking that why Earth has a magnetic field. I will tell you that in a bit as well. Okay. You can write this down, please. Okay. So it's like, if you put a magnet like this and you suspend this magnet freely, so Looks like magnet though. And suspend it like you attach something like a cloth or something, right, onto it on the other side as well. You just suspend it freely. You'll notice that the magnets poles would align with the Earth's magnetic field automatically, right? Now, I just want to tell you people that when you basically look at any magnetic field, so let's define magnetic field first. So within magnetic field, basically it is a region where a magnetic pole or a magnetic material or a moving charge. Now this moving charge is the key word here. I want to focus here. Stationary charges do not get affected by magnetic field at all right? It's just the um, moving charge that gets affected, okay? So moving charge experiences a force. So you can write that. Now, the magnetic field strength, just like electric field strength is like important, some people call this as magnetic flux density. Now, it doesn't have a particular
Or
density.
magnetic field is flux density and magnetic flux two different concepts?
Yes, it's different. All right. For now, you guys need to remember it's measured in Tesla, that is capital T, because of basically there was a scientist, Nikola Tesla. He has done a lot of work. Elon Musk has no relationship with this. So the symbol is B and the SI units are Tesla, capital T. You should write that. All right. Is it clear, everyone? Now, I just want to tell you that then the question is, why does Earth has a magnetic field? So the answer to this question is, Earth's core is made up of molten iron, lead, etc. By the way, so since Earth is spinning, right, the moving ions, which are the charges, right, cause a current flow, and this creates a magnetic field. This is why Earth has it, right? Now, the field is very weak as the flow of current is small. It's not very, large. So that's why you get a very weak magnetic field there. I hope you guys understand this, right?
Yes.
Now, please write this down so I can go to the next page actually. Now, I just want to tell you, people, that
Give me 2 more minutes, please.
okay, all right, you can write it down.
There is no definition for magnetic field strength like force exerted per unit of a particular object, or no?
There is a definition, but we'll do it when we learn the formula for this. Okay,
All right.
I've just skipped it for now. चार्जर नहीं मिल सकता सर वो पकड़ स्लो done. Okay, cool. Now, some materials that do get attracted to magnetic fields, they're basically known as the ferromagnetic materials. Now, ferromagnetic materials are materials such as iron, nickel, etc., right? Steel, etc., that get easily induced by magnetic field because they can, get attracted. For example, let me just copy this diagram. I need this. Wait a second. Paste. You guys can write this down, please. Okay. Now, in case you have, a material which is basically not a magnet, just a ferromagnetic material, like suppose you have cobalt. So basically, no matter what, whether it's north and south, it's gonna get attracted to it. All right, it's gonna move like that. Even if you put the same material, any ferromagnetic material, to the other side of the magnet, where you have basically north and south, it is still going to get attracted, because a magnetic material would also always, no matter what pole is there, it will get attracted. It doesn't matter like that.
Sir, why does that happen though?
Because these materials are not basically magnets, they're just attracted to the magnetic field. So whatever magnetic field comes near them, they just go through that, right? Is it clear?
And sir, what is the difference between magnetic fields and electric fields? Because the difference between electric and gravitation was that gravitation is only attractive. So what about this one?
Magnetic field and gravitation, electric field, basically they're both attractive, and you could say they will always be sort
Repulsive.
of repulsive, but they have huge differences in terms of what kind of materials they attract. For example, like if there is a stationary charge, electric field would cause a force on that. Magnetic field doesn't affect anything that is stationary. Do you get it? It doesn't affect stationary charge. It affects a moving charge like that. And usually both fields are 90 degrees to each other. They're never like parallel. Do you get it?
Yes, sir.
So they don't interact with each other as such. If they're parallel, they're very different in that sort of. But they do attract and repel. That's correct. Okay. So that's the thing. But if you basically put a permanent magnet, like for example, if there's a magnet that has a north pole and south poles, this is a permanent magnet I'm drawing. And this is south, this is north, like that. So it will get attracted. And the reason it gets attracted is because opposite poles attract. The thing is that if you put the same, magnet on the other side, and you have north here, south here, so they will get repelled. And the reason they're repelled is because same, or you could also say like poles, repel. Get it? Just like that. Very simple IG stuff. Now itself, when you look at these materials, you can draw this and then you're gonna go forward. I don't like this chapter, by the way. It's very boring. Maybe some of you might like it. Right. Okay. All right. Should I go forward, please?
1 minute, sir. Oh, let's say we can continue.
Okay. So now there are two kinds of materials, magnetic materials, that we can talk about. The first kind are called soft magnetic materials. Okay, the other ones are like hard magnetic materials. Now this doesn't mean that one is like literally hard or one is like a chewing gum. It's not like that. This, physically they're hard, but the properties are different. Like for example, the soft ones have their magnets of temporary nature of magnetism. So if there is a magnetic field close to them, some magnetism. All right. If there is a magnetic field near them, they get induced and they become magnets for some time. But then, as soon as the magnetic field is removed, or a magnet close to them is removed, they are easily demagnetized. They lose the properties quickly. So they can be easily magnetized or demagnetized. All right. Also, I just want to tell you, iron is one of those examples. So if you bring iron close to a magnet, it will become a magnet or magnetic field. As soon as you remove that permanent magnet near it, it is going to go back to the normal iron it is. Is it clear?
Yes.
With respect to the hard magnetic materials, I just want to tell you that they are magnets with a permanent nature of magnetism, which means once they become magnetized, it's very hard for them to be demagnetized. So cannot be magnetized or demagnetized easily. Then the example for this is steel. So the magnets that you see in the market, they're made of steel, not iron, because steel retains those properties. Is it clear?
Yes.
Okay, write this down. Once you're done with this, I also want you to write the direction of magnetic field. So direction of magnetic fields is basically magnetic field lines. Sorry. So I just want to tell you that they're hypothetical lines. So basically, we go through a convention on this, right? That depict the path of adopted by a unit hypothetical north. So it means wherever you leave a stationary north in the magnetic field, wherever it will go, you will just follow along that path. It will basically give you the magnetic field direction. Is it clear, everyone?
Yes.
Right. Write this down, please. I don't know how much space is left. Okay, I got to go to the next page. So I just want to tell you that if you look at just the single magnet, all right, which has obviously a north and a south. So outside the magnet, it basically oh no. It will basically the lines go from north to south like this, not like that, and like that, like this, like this. So they're always like north to south, by the way. The other things I would like to tell you is that one, the lines are distinct, which means they have their own paths. Number two, they do not intersect. So they do not cross each other. Remember that. So what I'm talking about north is that if you put, let's suppose a very small magnet which has a north here, south here. So the north would take up this path, like it will go here, and that is the reason we are taking this direction as the direction we're going to take. So this is just a, you could say, convention that we follow. Right? Is it clear, everyone?
Yes.
Cool. Write this down, please. Okay, you can write this. I'll be back in 1 minute. All right, kids. So should I go forward, please?
Yes.
Okay. So when you're making magnetic field lines between, like, suppose you have a magnet like this and another magnet like this. I should have made it a bit. Okay, and then we might also need this for two other setups. Let's do it here. Let's do it here. Well, that would not be okay. So we have to do it here then. Sure, no problem. Let's put it in the center then. Okay. So inverse. Okay, now the first kind would be if you have north here, south here, and south here and north here. So they would create an attractive field. You go like this, north to south, like that. Attract it. Then they will also go back to its own south, and then some lines in the south. This would also go like this and out from north like this. So You see, the number of lines that are made that come out from north would also be the same number of lines that go into the north. Okay, so you guys can draw that. Okay, then for when you have north and north, oh no, north and south, so this would create a sort of a repulsive field. So the lines would go out of the north, but they're not going to connect. It's just going to be like that. And they'll connect to its own south. Like this. In from south like that. So the number of fields that go into the south should match the number of lines that come out of the north, like that. Like that. All right, everyone? In the center, where you see this point, there's going to be nothing. So this is basically known as the null point. Null point means that there will be no field at this point, right? So no magnetic force acts at this point. You guys need to remember that. All right, everyone? Similarly, if you have the other one, south, north, north, so it's going to look like the same that we've drawn before, just that it will have opposite direction arrows. Again, just remember that this kind of field doesn't connect or intersect with other lines at any point. So in from south, out from north. Like that. And this would be the same null point at the center. Remember that, all right? Any questions, please do let me know.
No, sir, just let me copy this down, please.
Yes, you may take your time. All right, should I go forward now, you kids?
Yes.
Yes, sir.
Okay. Now, today, the last thing we're basically going to do in this is basically a very important side note. What you're going to do is you need to have a, suppose inside the magnet, you have north and south like that. I just want to tell you that when you draw a field, like outside, like I said, it's outside like this from north to south. Oh my God. Wait a second. Like this. So what I'm saying is that inside the magnet, the field basically is going straight like this. Do you guys get it? So actually, within the magnet, the field is parallel and there's straight lines. Do you guys understand? So let's write it down here. We're going to say inside a bar magnet, field lines run parallel and are equally spaced. Indicating a uniform magnetic field strength. And the other important thing is, as you can see, they run from south to north, not north to south, because they want to make complete loops. Do you guys get it? So it's basically in complete loops. It has nothing to do with north to south. Is it clear? Any questions?
No.
Okay, please write this down. This is also very important.
Done, sir.
All right. So I think the next thing we got to do was magnetic field strength, but it's all right. We'll continue this in the next class. But before you go, I want to basically tell you that on Saturday, 4 p.m.
Sir, we already have to have a test at school.
You have a test at school?
Yes.
When?
The first 2 chapters on Sunday.
On Sunday, so it's okay. So Saturday we'll have our test. Sunday 4 p.m. Pakistan time test. Okay. What chapter? Basically, if I remember, which I've discarded this. So, I have taken the test of
Thermal physics.
thermal. I have done thermal physics. So it means that we need to take a test of electric fields.
Understood.
Yeah, electric fields test. Let me write that down. Electric. Those people who have not done this, they can skip this one. But most of you, I think, have done this, so you guys should take the test. Electric field test on Saturday, 4 p.m. Pakistan time, on 30th September. All right. Okay, do remember about that. So you have a couple of days to prepare for that.
Maybe on Saturday, sir. At that time, I won't be at home. So is it okay if I submit it by Sunday?
I will also not be available on Saturday 4 p.m.
Okay, you can submit it on Sunday, no problem.
Okay, sir.
All right. See you then.
Allah
Bye.
Hafiz.
No problem.
Thank you.